Okay, so in this question, we've got a Carnot engine. It's going between a hot reservoir with a temperature of 700 kelvins and a cold reservoir with a temperature of 300 kelvins. And the work done each cycle is equal to 1,100 joules. And each cycle lasts 0.25 seconds. So this T stands for period here. Okay, and in part A, we're asked, well, what's the efficiency of the engine? So we know that for a Carnot engine, the efficiency is given by 1 minus the temperature of the lower reservoir minus the temperature of the higher reservoir. So this is 1 minus 300 over 700, which is 1 minus 3/7, so that's equal to 4/7, and then you needed to enter it in as a decimal, so as 0.571, and efficiencies don't have units. Okay, so part B is then what is the average power of the engine? Okay, so power is given by energy over time. In this case, the energy we're getting out is the useful work. So this is equal to 1,100 over 0.25. Solving this, dividing by a quarter is the same as multiplying by 4. So we've got 4,400 watts. C, we're then asked how much energy is extracted from the hot reservoir each cycle. So probably the easiest way to do this is using another one of our efficiency equations. So when we initially defined efficiency, we said efficiency was equal to the amount of work we get out, so the useful work we get out, the work, over the amount that we pay for, which is the heat from the hot reservoir. So since we know the efficiency and we know the work that we get out, this is the easiest way to find QH. So QH is equal to the work we get out over the efficiency. So that's equal to 1,100 over 4/7. And solving that on the calculator, we end up with 1,925 joules. Okay, part D, how much energy is delivered to the low temperature reservoir each cycle? Okay, so in order to do this one, probably the easiest way to do it is to remember that for a Carnot cycle, the work out is equal to the difference in heat which it receives from the hot reservoir minus the heat that it gives up to the cold reservoir. So we can rearrange this and write QL is equal to QH minus W, and so this is equal to 1,925 minus 1,100, and so this is equal to 825 joules. Okay, and part E then asks us what is the entropy change of the working substance as a result of the energy transferred to it from the hot reservoir. Okay, so first of all, we're trying to work out the entropy change from as the heat's transferred from the hot reservoir. So we know that for isothermal processes, which is what this is, we've got that the change in entropy is equal to Q over T. So this will be QH, which is positive, over T. So QH was 1,925. The temperature of the hot reservoir is 700. So solving that, we get plus 2.75 joules per Kelvin. Okay, the question then goes on and asks us what's the change in entropy as it transfers heat back to the cold reservoir. So there's a couple of ways we could do this. We know that round the cycle, the total change is 0, so it should just be minus 2.75. But we can also do it as QL on T just to check our working and that our other answers make sense. Now it's giving heat to the cold reservoir. So this is a heat transfer out of the working substance. So we give it a negative sign because it's losing that over the temperature. The cold reservoir is at 300. And solving that on the calculator, we get minus 2.75 joules per Kelvin. So we can be happy because that's what we expected.